Okay, welcome back. Let's start our next lesson. This is the vSphere API array integration lesson. So what does this mean? You'll find we have a couple lessons that talk about the different vSphere APIs. This one is typically known by its four-letter definition, VAAI. So what is VAAI, otherwise known as the vSphere Storage API for Array Integration? This is basically one of our hardware acceleration and thin disk provisioning supporting offloading capabilities here. So one of the really powerful features of this thin provisioning API support is the other enhancement to VMFS 6, and that is VMFS 6 supports something called space reclamation for thin provision storage. That's big. So vSphere APIs, there are, like I said, several APIs we'll be taking a look at here. This one though, the vSphere Storage API for Array Integration, I know that's got several words that seem extra compared to what we usually refer to this. We usually refer to it as VAAI. This is an API that is built into the VM kernel, right? So there's nothing you need to install on vSphere. vSphere is ready to go. It's got this built in. But what VMware did was work with the storage vendors to be able to provide some offloading characteristics onto storage. So that means that your storage vendor would also need to have this API implemented there as well. Whether that's a firmware update or however you're going to update API access on the storage side, that is something that needs to be implemented on your storage before being able to take advantage of this in our vSphere environment, right? But basically, once that's been put in place, that your array has now supported and has implemented VAAI, so then you're able to leverage two really important capabilities: hardware acceleration and array thin provisioning support, right? These are two really big things. The hardware acceleration basically integrates vSphere into having transparent offloading on certain storage operations on the array. That significantly reduces CPU overhead on your ESX server when it comes to storage I/O. And then the array thin provisioning APIs, they help prevent what's called an out of space condition and perform space reclamation. This was actually a bit of an issue if you don't have an ESX server who has this knowledge of what the array is being presented to the ESX server. So basically, this API is a set of protocols the VM kernel has built in to integrate with our storage to make these things happen. So let's take a look at these. In our first case, hardware acceleration for block storage. This has actually been first implemented way back in the old vSphere 4 days, so it's been in the product for some time. It actually was introduced in vSphere 4.1. These APIs significantly reduce the CPU overhead on your ESX server when it comes to storage. This works with fiber channel storage, iSCSI storage, anything that provides block storage from the storage array side, right? Not local disks here, but things that are coming from a SAN side, whether it's fiber over Ethernet, or iSCSI, things of that nature. And this basically allows for our block storage devices to support several array operations behind the scenes transparently. So what are they? There's basically three basic primitives that the hardware acceleration provides. So the array is doing these for the ESX server, right? Or on the ESX server's behalf. Right, so those are three primitives typically known by, usually by several names. The first one is known as full copy, also known as clone blocks, sometimes known as copy offload, or sometimes simply known as xcopy, right? So several definitions here, but basically what it means is the array is able to perform a LUN-to-LUN copy without interfering or involving the ESX server. Imagine you're trying to perform a storage vMotion from one LUN to another LUN. Typically what that does is the ESX server has to read in the virtual disk and all the VM data from the source LUN and then probably write down the same path to the new LUN location. So that's going to incur a lot of overhead. The host has to both read and write the same data in two different locations. If the LUN can perform the LUN-to-LUN copy, that saves a lot of overhead on the host. Same goes with cloning. You need to clone a VM from one LUN to another LUN. If we can let the array do the cloning, this offloads a lot of operations for us. Or deploying a VM from a template, same thing. So that's one really nice thing, right? The LUN-to-LUN copy feature. Then there's also a mechanism called block zeroing, or also known as write same. Basically what this is offloading the ability to fill blocks with zeros. My goodness, what are we talking about here, right? Whenever you have an eager zero thick disk, what happens? When you have an eager zero thick disk, this is a disk that has had all of its disk blocks allocated, right? Well, that's something that the host is going to provide. But then filling those blocks with zeros, that's a fair amount of overhead on the ESX server. If you ever try to see the difference in how long it takes to create an eager zero thick disk versus creating a lazy zero thick disk, if you were to do these operations with two disks of the same size, the lazy zero thick disk will take a lot less time to create, because all we have to do there is allocate the blocks, and then the blocks get zeroed out when they're accessed for the first time by the virtual machine. Eager zero thick disks, on the other hand, all the blocks are zeroed out up front when you create the disk. Well, if we can let the array do that for us, this makes the creation time for eager zero thick disk much, much faster. And then finally, a much more significant one here is known by several names. Hardware assisted locking is one name. It's also known as atomic test and set, sometimes even known just by its abbreviation of ATS. Another way you could refer to this is basically offloaded LUN reservations. Imagine every time you power on a VM, what has to happen with the blocks that belong to the files for the VM's files, right? You power on a VM, all the files that belong to the VM need to have locks applied to them. Well, in order for an ESX server to establish those locks, normally what happens is the host is going to perform a LUN reservation operation, which basically gives that ESX server exclusive access to that LUN while it's establishing all the locks on the files that belong to the VM that they were trying to power on, or snapshot, or suspend, or resume, or vMotion, right? Or any type of administrative actions on the file system. Those also incur a LUN reservation. For a host to get its exclusive access to perform these actions, it'll need to perform a LUN reservation. Now, LUN reservations are short-lived, so they aren't something that are things that take forever, but while that LUN reservation is actually in place, no other ESX server can actually write to that storage. That reduces a lot of performance on other hosts in a large distributed environment. If we could actually do this a much more granular and offloaded mechanism, well, this atomic test and set will actually allow for that, letting the array perform the actual allocating of the disk locks at the disk block level. Right, so this improves the VMFS for metadata changes. I know that sounds a nice generic name, but really what that is, it's just basically anytime that metadata changes for a VM or for the VMFS file system, that's typically incurring a LUN reservation, where with this atomic test and set, that basically is then mitigated. So this is for block storage, of course, right? This means that any file system that is a VMFS file system, typically on an array. Now, the NAS environments were updated to support this in vSphere 5, right? So this isn't quite the same, all right? But to do hardware acceleration for NAS, there are several primitives that are somewhat similar, but not quite the same. For a NAS, there's the ability to offload the full file clone operation. That means the entire file, when you need a copy of VM from one volume to another NAS volume, is done at the entire file level instead of being done at individual file segments, reducing a lot of overhead. There's reserved space capability. This is interesting because a NAS typically provides thin disks in its storage environments. By providing this hardware acceleration for NAS means that you have the ability to create a thick disk in a NAS. And there's also native snapshot support. So for environments like Horizon, where you can offload the creation of link clones into the NAS array. And of course, this also, with this hardware acceleration for NAS, allows for extended file statistics. So that was a quick look at one set of characteristics that you get with VAAI. Come back in a few minutes, and we're going to take a look at how to take advantage of thin disk, or I should say thin LUN provisioning support as well. So we'll take a look at that when we come back from a break.